Hi, everyone. Thank you again for joining us for the What's New in UALink Technical Deep Dive into the latest UALink specifications webinar. If you go to the next slide, you'll see our speakers for today's webinar, which include Derek Williams, Dave Brown, Justin King, Arun Satyanarayana, and Rob Pelt. With that, I'll go ahead and hand it off to Derek to kick off the presentation.
Good morning, everyone. I'm going to talk about the UALink Common Specification first, and then hand it off to talk about the DLPL with Dave next. The big changes in the UALink 2.0 specification, the first major change is we've factored the specifications into a 2.0 common specification and a DLPL specification in their own documents to allow for multiple DLPLs. The common specification will cover the layers above DLPL, TL, UPLI, and other overall aspects. The second major change in the 2.0 specification is the addition of support for in-network collectives, which allow the offloading of some data movement and computation tasks from the accelerator to the switches. UALink is based on the notion of UPLI interfaces. UPLI interfaces have 4 channels. A request channel, originator data channel. Request channel contains the request. The originator data contains the data for writes and the operands for atomics. The read response channel contains the read status response and read data response for, for reads and atomic Rs, atomics that return data. And the write response channel contains the write status for writes and atomic NRs, or atomics that don't return data. This interface is a flat, wide collection of tens to hundreds of signals that make up this interface. To build out UALink, we take 2 of those interfaces in an accelerator, an originator, and a completer, a bidirectional pair of those interfaces. The originator is sourcing requests in this direction, and the completer side is receiving requests in this direction. So this is a pair of bidirectional symmetric UPLI interfaces that drive commands and responses. Those are received by a transaction layer, or a UALink TL, that takes these interfaces and packetizes them into 64-byte TL flits at this interface and passes them to the DL layer. The DL layer takes the 64-byte TL flits and packs groups of 10 of those into 640-byte DL flits that are then finally passed along to the UALink PL and SERDES, which pass them over the link. Obviously, the same set of steps happens in reverse for the inbound traffic. The SERDES creates a 640-byte DL flit, goes to DL, creates a 64-byte TL flits that are then unpacked and pushed onto these interfaces as the request and the rich data channel to the completer and the responses to the originator. This figure illustrates a full accelerator to accelerator connection. We'll start here with one UALink stack component on the accelerator, connects over a link to another UAL stack component on the ingress side of the switch, with a switch core in the middle that unpacks the TL flits and the UPLI requests and switches them to the appropriate destination accelerator. We go through a second UALink stack component here, over a link through a final UAL stack component to the originator and completer interfaces on the destination accelerator, ultimately. This figure illustrates a full UALink system. We'll have in accelerators, in this example, 64. And we have 60, in this case, we have 32 ports per accelerator. Each one of these ports is also, the ports are grouped into a station, A station corresponds to a UALink stack component. The number of stations and ports you have does not have to match the number of accelerators. The station can also be a single port, 2 ports, or 4 ports. For this figure, we've illustrated 4 ports. Each accelerator connects to every switch via one UALink link, and each switch, therefore, connects to all accelerators, but only once on one link. Okay, so this is the basic topology and the interconnect of our system. Let's consider a write request for a moment here. A write request a normal write request starts with a request from the accelerator. In this case, to switch 0, it goes out arbitrarily, goes out station 0, port 0, goes to the switch. This request, just in this example, is destined for accelerator 33. So we have one request to get the request from the accelerator to the switch. We have another request to get it from the switch to the destination accelerator. When that accelerator is done with that write request, it sends a response back to the switch, and then the switch forms another response that is sent back to the ultimate destination accelerator. So the key thing to remember from this slide is that every normal read and write consumes 2 requests and 2 responses. For a write, the request is where most of the bandwidth is because that's where the data is, and the responses are rather small. For a read, it follows this same pattern of request, request, response, response, but the majority of the data bandwidth consumed is in the responses because those are delivering the data back to the initial accelerator. So, collectives. What are collectives? UALink defines a collective abstractly as a set of accelerators. We also call that a group. And where each accelerator within the group is also referred to as a rank. In each rank, there are input and output data arrays on each rank. The input and output buffers may be located at the same location in memory. We call that an in-place collective, or they may be at different locations, but the input and the output arrays for a collective may not partially overlap. They have to either be fully distinct or exactly on top of each other. And in a collective reads, you read from one or more of the input buffers, depending on the collective. You process the data through a reduction function if that data is read from more than one input buffer. And then you write to one or more output buffers. So that's the general abstract notion of a collective. We illustrate here 3 main collectives: broadcast, reduce, and all reduce. So let's look at broadcast. Here's an example of broadcast. Rank, we have 4 ranks. The root rank, the rank issuing the command is rank 1 in this case. It has an input buffer that's going to be read of send buff count elements. That buffer is going to be replicated and written to an address receive buff on all 4 ranks. Okay, so we take this input array, we replicate it to each rank on each, or replicate it to the output buffer on each rank. So this is the simplest of the collectives. Another way to illustrate that and look at that is, here's rank 1, the root rank with its input buffer. It's broadcasting to all the ranks in the group, including itself, because the destination buffer might be different. In the case where the destination buffer is the same, it's not, in the case where the buffers overlap perfectly input to output, the write to the root rank can be deleted and removed because it's already there. So that's broadcast. The next reduction is reduce. Our collective is reduce. And in reduce, we take data from all 4 ranks, or all the ranks in the group, at a given location. We run them through a reduction function to produce a reduced version of the input data, and we write it to the output buffer on the root rank. And we do this for each data element in the input array. 1, 2, 3, 4. Okay. Looking at how that's illustrated here, since the output data is different than the input data, you've always got to do the write to the final output. You take the input buffers, run them through your reduction function. A reduction can be an add, it can be logical ORs, floating point adds. There's a number of them illustrated in the specification. And you produce your output buffer on the root rank. There's another collective. The next collective is called all reduce. All reduce does the exact same thing reduce does, except you write the outputs to all ranks rather than just to one rank. Okay. Again, if the send buff equals the receive buff, the operation is an in-place operation. And the other way to illustrate that is, here's our input buffers, our input ranks. They all run through the reduction. And we write to excuse me, we write to all of the output buffers. So UALink provides two mechanisms to implement collective primitive, the abstract notion of a collective primitive. The first of those are to implement the abstract notion of a collective. The first way we implement collectives is a mechanism called collective primitives. So a collective primitive is a read, a write, or an atomic operation that's issued by the requesting accelerator to a switch that the switch then replicates to all of the accelerators within the group. Now, we'll see later, we'll use read, reduce, and writes to implement, excuse me, to read, reduce collective primitive will be used to implement the reduce and the all reduce collective, and write multicast or write full multicast will be used to implement the broadcast collective, okay? The atomic NR multicast isn't really used to implement a collective. It's used to write flags at all the ranks and update flags to help synchronization and delineate when collectives have been finished processing. So to implement the broadcast reduce or all reduce collective, we use a loop or loops of write full or write full multicasts and read reduced that will iterate through the arrays. The collective primitive offloads the iteration across the ranks. So for a collective primitive, the switch will take care of the different ranks, but the software and the accelerator still needs to iterate through the array. So let's look at an example of a write multicast. In the write multicast, we have a write multicast, in this example, going from accelerator 0 to switch 0. The group that it's involved in, which is, there's a switch in the table delineating the group membership and for which of the numbered groups, which accelerators are in it. In this example, we're going to show all the accelerators being in the group. So the write multicast request goes to the switch. The switch replicates the write and sends it here, request 01 through request 63 to all of the accelerators. Now, the useful part about this is this collective primitive only needs to do 64 requests to do the writes to the accelerators. If you were going to do 64 writes from this accelerator directly, it would have to do 64 writes to switch 0 that then made their way across to 0, 1, 2 through 63. So this reduces the bandwidth by about a factor of 2 over what you would need to get this done with a normal write command, okay? Once those writes have gone to each accelerator will produce a response. All 64 of the responses will be sent back to the switch that issued the requests. Those will get aggregated into a single write response that then gets returned to the accelerator. Again, we only need 64 responses as opposed to native writes, I should finish this, which would need 128 responses. There would need to be, if you did a normal write from here to here, like we showed that initial thing, there'd be a response back and then a response back, whereas here, all 64 of these are combined into one response instead. The second mechanism we provide to implement collectives is something called a block collective. In a block collective, we are going to offload the entire collective, broadcast reduce and all reduce. Those are the three that are supported. The entire thing is offloaded to the switch. So in this case, the switch manages the iteration both through the ranks and through the input and output arrays. So this is a one-time fire and forget command of the switch. The switch will, and that's called a block collective invoke request. That block collective invoke request delivers a 64-byte control block that describes the collective to the switch, and then the switch goes off and runs through the entire collective. It reads all the ranks as necessary, getting the data, or reads whatever ranks are necessary, getting the data, and then it does all of the writes necessary to deliver the data to the output buffers. Once that's complete, the switch does a write to update a status buffer on the root rank to indicate the completion of the block collective. Excuse me for just a second. Okay. Block collectives, improve over collective primitives, improve over normal reads and writes in the same way that collective primitives do. They get that same sort of 2x effect that a collective primitive does, like we saw here, where we just do the 64 requests and 64 responses. Because we're issuing the commands from the switch, we get the same sort of bandwidth reduction in a block collective. Both block collectives and collective primitives improve on using native reads and writes because they offload to varying degrees the amount of work that the accelerator, the amount of looping and iteration the accelerator needs to do. This figure illustrates the relationship between the different collective primitives and block collectives. To implement a broadcast collective, you can do loops of write multicasts, which would give you the effect of a collective. For a reduce, you can implement a loop of read reduces to give you the reduce collective, or you can just implement broadcast and reduce directly using block collectives. And all reduce, because it is really a reduce, and all reduce is really going to do, a read of one rank, a read of all the ranks, get the data, and then it's going to do a series of broadcasts to write all of the ranks. So as you can see here, to implement an all reduce, we do a single reduce back to the root rank that gives us the reduced array, that's the output. And then we do a broadcast to the remaining, a broadcast which will write the data to all of the ranks. It will write the reduced version of the data to all of the ranks. There are some backup slides here that illustrate some more exotic, I'll call them collectives. All gather takes an individual element of data from each of the ranks and creates an array, replicated array at each rank of each of those individual pieces. Reduce scatter adds up, much like reduce or an all reduce adds up each column of these elements, but then places the results only for each element in a position on each accelerator. So we do not support either of these directly as block collectives. They have to be done with software loops with the existing primitives. These slides illustrate how you implement all gather as a number of smaller broadcasts and how you do reduce scatter as a smaller set of reduces, and how you implement all reduce as a as a single reduce and a broadcast, as we discussed later. And this is the same slide we saw earlier on the relationship, except that adds these two elements down here for how you would build reduce scatter and all gather. And with that, I believe it is time to hand the baton over to Dave to discuss the DLPL.
Thanks, Eric. All right, so we'll talk about the 2.0 new features for the data link layer and physical layer. So here's a summary of the various things that we've added at 2.0. So there's several batches of errata that have been included. There's an ECN for DL down delay, an ECN for link resiliency, ECN for link folding, an ECN that added the CRC example into the appendix. And the last ECN was to talk about the interface between the DL and PL. And both of the last two were informative. Okay, so DL down, that was one of the, I believe that was the first ECN that we introduced. And that really came up around from the concerns of link flapping. The way it was originally specified was if the physical layer ran into a fault condition where, say, it got a few bad code words in a row, that would cause the PCS to start hunting for a new alignment. That would take the link down, which was a fairly big impact to the system. That would require restarting the system and backing up to the latest checkpoint, which is a pretty big impact. So we came up with the idea that we should really have the ability to kind of tolerate the physical layer needing to regain alignment without taking the data link layer down. So we introduced ECN that would allow up to a 10 millisecond interval where the physical layer is in a fault state. And as long as it comes back from a fault state within that 10 milliseconds, it's a programmable timer, but if you've got it set to the max, it would be 10 milliseconds. As long as the link comes back, then if the physical layer comes back within that timeout period, then the link stays up. And the amount of time typically it takes the physical layer to come up would be in the order of several hundred microseconds. The alignment markers are spaced under microseconds. I believe it takes around 3 or 4 of those before the alignment is regained. And that would also allow enough time to do other things, perhaps resetting the CDR lock circuitry on the receiver as well. Typically, that can be done within a few milliseconds and then get the link back in an operational state. Link resiliency was another ECN that we added. Again, that was around the concerns of link flapping and potentially link going down and not being able to be recovered within that 10 millisecond maximum timeout. So the concept here is that there be 2 physical layers associated with each transaction layer and data link layer. As long as one of those physical layers stays up, then the link would be in a up state, and you could still run traffic, albeit at a 50% throughput during the time that the one physical layer is down. And that gives a little more time to attempt to get the physical layer that has lost alignment to be recovered. You could go through more. Potentially even do a link retraining as well as a CDR reset. One other thing we needed to do was add physical layer IDs to the alignment marker, and that is so within the alignment marker control flits. There's we took one of the bytes there and added whether which physical layer it's from, and that's recorded on the receive side to determine the ordering of the flits when they're merged back into a single stream for the data link layer logic. Right. So one of the on the receive side, we need to make sure that we get the same ordering on the transmit side. So the requirement that the DL provides in order delivery of the DL flits that were consumed on one side or then regenerated on the other side, that requirement is maintained. Another thing, we needed to keep a link state machine essentially for each physical layer. So as long as one of those link state machines is in the up state, then the link is operational. If they both go into link down state, then the link is down, and we're in that situation where we would have to reset and then go back to the latest checkpoint to restart. And conceptually, this is a way of looking at the transmitter. We've got a single transaction layer. For the most part, it's a single data link layer. The packing is the same. What's different again is what I said before, the link state machine. There's 2 of those, one for each physical layer. And right just before you transmit out those DL flits, there's a ping pong buffer. So basically, we're doing flit interleaving on the transmit side. And also notice that we have a half flit time offset. And the reason for that is just to minimize the latency in this ping pong buffer in the transmit. It basically adds about a half flit time of latency with this mechanism. And if you had them synchronized, it would add more. And as I said before, yes, each of the alignment markers have a physical layer ID. embedded in them. So here's just a timing diagram at the bottom here. You can see there's multiple idle flits being sent. This would be, say, during initial link up where you've got idles on both sides. And you can see alignment markers are set such that physical layer B is staggered a half flit time behind physical layer A. Same idea on the receive side. We've got the two physical layers. You can see the PMD, PMA, PCS, RS, the reconciliation sublayer, and they feed in logically. You can think of them feeding into two separate buffers. And then on the read side, you've got to pull them out in the correct order. So one of the things that you would need to do on this receive side, they could be coming in with some unknown skew. You've got to look for these alignment markers and also look for the physical layer IDs and then align them in the right order, and then you can start pulling them out the correct way. And here I'm just the bottom of this timing diagram. You can see the sequential numbers, and those would be the sequence IDs in the header that is used for replay. Okay, so link folding basically builds on a link resiliency feature. It's a power savings technique if we know that the link is not being utilized. A lot of the link utilization tends to be very bursty. There's a period where it's very busy when you're exchanging data for collective, and then there's generally a GPU compute time where the link is not used significantly. So during that period, you could fold the link down to save link power and use that power that you're saving on the CERDES to run the GPUs at a higher clock rate, for example. This is only supported for the 200 gig serial rate. And obviously both sides need to support it, and you also need to have supported a link resiliency to use this feature. Right. So the entry and exit is negotiated by DL messages. Similar for anyone who's looked at the UALink 128 gig, there's messages there that we use for changing the link width or link speed. It's the same, conceptually the same idea here for the UALink 200. We introduced a power down control flits. That's something that the RS generates, and that's used to synchronize when both links are going to go into a power down state. And another thing we added is rapid alignment markers, which conceptually are the same as what Ethernet uses, although the implementation is a bit different. And the idea there is to speed up your exit time when you're turning that other link back on. If we left just the regular alignment markers, it's 100 microsecond intervals, you'd be adding 300-400 microseconds to the exit time, which would impact your ability to save power. You'd be having to turn that link on sooner than you otherwise would need to. And on the left here, we just got the ladder diagram where you can see the negotiation that's done, the link width request ACK, and then the corresponding ACK. So that's done at using deal messages at the sort of consolidated deal level. So those ACKs and requests could actually be sent out on either physical layer, it doesn't matter. Once we get into the power down state, part of the negotiation for which physical layer you're going to turn off would be indicating, hey, I'm going to turn off physical layer A or physical layer B. So whichever physical layer has been agreed to power down, that's now sends these power down control fits. So that's generated by the RS. And once each side has sent power down control fits and received a certain number of power down control fits, at that point, it is safe to turn off the transmitter and receiver save power primarily in the SERDES. And you can see on the right-hand side, we've got this link state diagram. So what we've added here is the DL power down state. And that's what's used to turn off the physical layer that you want to save power on. So remember, there's two of these link state diagrams. So just the link state turning off would go from a DL up to DL power down. And this DL power down state is where the power down control flits are sent. When you want to exit power down, there'd be a transition to DL fault. And similarly, because we've still got one of the physical layers operational, we can send a link width request to turn on that physical layer on the adjacent physical layer. So once that's negotiated, then each side would transition from power down to DL fault, and then that physical layer and the associated DL state machine for that physical layer would then move up to the DL up state, and then both physical layers would be able to carry the full traffic for the link. Okay, so one of the things we added as well was a DL PL interface, and that's informative. Means it's not required by the spec. And really the purpose there was so that VIP vendors and IP vendors who wanted to develop the physical layer independently of the data link layer could do so and have interworking. There's a lot of IP providers have Ethernet IP, and the modifications to add the RS for UALink is relatively straightforward. I'd say compared to implementing the DL and the transaction layer, all that is all brand new IP, which generally is a little more work. And also, I know at AMD we found it quite useful with the various VIP vendors to help in our system integration, being able to perform different loopbacks and test each piece of IP independently. So I would strongly encourage people to make use of this interface and the various VIP that will support that. Right, what else to talk about? Right, so it's a TDM interface similar to the UPLI, which is a TDM interface. You can configure that as 1, 2, or 4 ports. On the TIX interface, it's a valid ready interface. The physical layer basically pulls flits because it needs to always be sending code words, and it needs to match either a control flit or a data link layer flit into that control word. So when the physical layer says it's ready, the data link layer must produce a DL flit at that time. 500 default bit data path. Obviously, the PL needs to indicate the start of the code word because we're matching each flit fits exactly into code word. So the DL needs to know when to start shipping that. Otherwise, you're putting additional latency into the physical layer to buffer it on the boundary. So we don't want to do that. On the RX side, a similar interface. It's just a valid interface. The DL must consume at line rate. And I think if I recall, there is a ready signal there as well, but it always has to be ready to consume the data. Again, same data path with 512. And the physical layer indicates the flit start timing, so the DL knows how to demarcate one DL flit from the next. And there's a few other details in the spec, but I'm not going to go into all that detail here. Okay, so I guess you're next, Justin and Arun.
Hey, thanks everyone. I'm Justin King, and Arun and I chair the Systems and Manageability work group inside UALink, and are responsible for the UALink Manageability specification. Manageability specification 1.0 aligns with the 2.0 common standard. and is available on the UALink Consortium website. And the manageability specification defines a lot of the system design, whether that be pod controller, the local management agents, protocols, interfaces, data models, the control protocol out to the switch management. And we are actively working on the redfish data model as well. As a sort of fundamental, UALink systems are grouped into pods, and we've defined a UALink pod as consisting of a set of system nodes with a host CPU and the accelerators on the UALink fabric, as well as a number of switch platforms hosting physical switches that are routing traffic. And of course, we continue our support of scale up to 1024 accelerators. I'm going to show one particular topology of systems here, but other topologies are possible. They're encouraged. This is an open ecosystem, and we encourage people to take advantage of the flexibility we're providing. Now, in terms of units for tenant consumption, right? We can break down a physical pod into virtual pods. That's what's demonstrated on the diagram here. That virtual pod is the unit of isolation. It's the unit of workload scheduling. So if you want to break up your physical pod, that you would create virtual pods to accomplish that. And a virtual pod can scale as large as the physical pod. They could be synonymous, and that may be the use case, or the use case may be many smaller virtual pods, just depending on your particular application. And these virtual pods are isolated from each other using routing entries that are programmed into each physical switch. So as Derek was talking about earlier, we have a concept of switches or logical switches that can enable multiple planes of routing between the accelerators. The diagram on the left here shows a way to connect accelerators through two routing planes, either by using two physical switches or by instantiating two switches on a single physical switch. And then that permits bandwidth aggregation. We can use the bandwidth of all of the ports by creating multiple switches. The diagram on the right really shows how we accomplish isolation, and that's by programming the routes into the physical switch so that traffic goes out a known port given the source and destination accelerator IDs and the port that the traffic came in on. So that's about isolation. I'm going to turn it over to Arun to talk about the system view.
Thanks, Justin. So the overall, so if you put what a pod is and how it is managed, you arrive at the overall system view. We've taken the approach of SDN style centralized control plane, which also extends the management and telemetry plane. So you have a UALink pod. It's got a bunch of accelerators up to 1024, and each of the accelerators, or one or more of the accelerators, sits on what is referred to as the system node. And then you have a switch platform, similarly, one or more UALink physical switches. So those are the two platform types. And then you put all this together into a pod, needs to be controlled and managed. And that's done through a pod controller. So we don't get into the high availability aspect of a pod controller in the initial version of the spec, but we do expect implementations to support it. But effectively, you have a fault tolerant pod controller that is discovering a UALink pod or verifying what a UALink pod needs to look like. And then it manages, or rather controls and manages the pod itself. There are a couple of pathways we have defined with respect to what the protocols look like. So each of the platforms, the accelerator and the switch platforms, need to host a local software agent, the NMA and SMA. And the interfaces and protocols are in the slide. The pod controller to an SMA is an extension to GNMI. So GNMI is an open standard that's based on gRPC, which is again an open protocol that's been available for some time, and it's used in the networking world. We've extended GNMI, which is predominantly a management interface, with a control RPC. And the control RPC is a bidirectional RPC that allows us to do a proper control protocol, but reuse other constructs in GNMI and the data model itself. The pod controller to an NMA, there's already incumbency there with respect to Redfish, and we are working on extending the protocol and the data model on that half of a physical pod. We've also specified a switch abstraction interface, SAI, kind of inspired and influenced by OCP SAI. But we do have quite a few differences from OCP SAI. We call it UALink SAI. So that's basically the interface definition that's running. So there are two halves to it. There's the upper half, which is the switch management agent itself, or the SMA. We expect that to be a common implementation. And then the lower half of the SAI interface is SAI implementation that's typically going to be vendor specific. And that ends up talking to the actual physical switch firmware to be more specific. We have not specified what that protocol between the SAI implementation and the switch firmware looks like. That's up to the vendor. And then the rest of it is GNMI, as we talked about. As I mentioned earlier, the management plane, the telemetry plane, and the control plane are all GNMI for the switch platform itself. So it's a unified set of protocols, gRPC, GNMI, and then YANG models for the data model. And on the system node side, it's also equally unified with respect to using Redfish and extending the Redfish data model. We're also looking to extend Redfish protocol a little bit. That's work in progress. So with respect to what the data model looks like, this is a summary or our philosophy to defining what that needs to be. So there are 4 groups. There is identity information, which is completely immutable. Things like serial number, you could have a UUID for a switch or an accelerator, port IDs, which are port nums, which are typically fixed for a given switch implementation. There's a vendor ID, very much like how a PCIe vendor ID looks like. Port counts on a switch, for example, they're all immutable bits of information. So that falls into identity, purely read-only. And then there is configuration data, or the group itself. As said here, it's configuration. So it's read-write. The pod controller would typically read identity information, would be able to configure use any of the bits in the configuration group itself. So a couple of interesting bits there, other than typically what the admin state is, right? You can have admin state for each of the protocol layers that Derek went through, and then we also allow the configuration of the accelerator ID itself. That's an important bit. It's a 10-bit ID, which is where the 1024 limit on a pod size comes into play. That's carried on the wire. So the protocol aspects that Derek went through carries the accelerator ID, and that is configured through the pod controller via the pathways we're defining here. And then there's operational state, things like port hopper state. We also allow neighbors to be configured. So neighbor state would also come into play. When I say port hopper state, each of the layers, each of the protocol layers that we've talked through. And on top of it is the telemetry grouping. So telemetry is almost always periodic information. Statistics would fall into this, but within telemetry, there would be typically two subgroups, or at least we are defining it that way. There is some gray area there, but you have normal metrics like TXRX, bytes, flits, drop counters, and equivalents, and then you have error metrics. We separate the normal metrics from error metrics because typically you expect less errors to come through, so we can get some amount of data compression when you're trying to send periodic, when you're trying to do periodic publishes of telemetry data. Yeah, as I touched on earlier already, one of the critical design goals we went with was that we would combine or consolidate the control management and telemetry planes here. So a single implementation can cover all of it on the switch platform or the accelerator platform itself. Yeah, so what does a pod controller look like? Centralized pod management, similar to SDN, like we talked about. A single pod controller can control multiple pods. It's up to the implementation. We don't define what that looks like. We are only scoping the spec to define what the interfaces look like. But a pod can only be managed by one pod controller, right? This goes into the high availability aspect. We don't have concepts like active standby intentionally. That's up to the, like, if you have a quorum or if you have active standby or active, whatever you want to implement on the pod controller side, it's up to that implementation. But at any point in time, an SMA or an NMA will accept one authoritative connection. And if you look at the SMA in particular, the GNMI control RPC, there can be only one active control RPC that an SMA will accept. Failover and related resiliency aspects are left up to the implementation of the pod controller itself. And then what are the functions of the pod controller side? This is almost sequential, and it's how the control protocol also fits in, and you can take a look at the spec for the details on that. We'll do topology discovery. So that's effectively all the SMAs and NMAs that are available that are fronting a pod itself. And then we do configuration with respect to switches and ports and neighbors. And then there is overall pod state tracking that also is both actual state and telemetry. And then it gets into vPod management. So a tenant comes in, asks for a subset of the pod for their workloads, that forms a vPod, and the pod controller creates a vPod, assigns the specific ports to the necessary vPods, and then sets up routing to ensure that there is no communication possible beyond the boundaries of a vPod. So like what Justin mentioned, a vPod can be 2 accelerators, but can contain all the accelerators in a pod as well. The northbound API on the pod controller, we don't define it, but we expect it to at least contain pod state and monitoring APIs for tenants and other ecosystems, other systems to consume. And then you have the tenant job itself, right? So typically, we expect the pod controller to be owned and managed by the CSP, the cloud service provider, or whoever is the admin function managing a pod. And then and the pod controller provide APIs to create vPods, delete vPods, provide state for vPods, and related information. And I think after this, can we go to the next slide, please? Yeah, so this one is a little bit of a blown up view on the SAI interface itself. We typically expect one SMA instance per switch platform managing multiple UALink switches, but an implementation can choose to have multiple SMA instances, one per switch. That's allowed as well. Just has to be a unique identifier, typically identified through its IP address. is what we would get to. And then I kind of touched upon this already in the previous slide. What a pod controller will manages the switches. Can completely disable a switch, for example, or set up specific modes the switch operates in, and then it sets up all the ports, can disable ports for a number of reasons: power saving, not utilized right now, failures, and related reasons. And then you can either discover neighbors, in which case you can trust a pod and say, okay, I'm going to just discover all the neighbors on either end. The accelerator has the switch as a neighbor and vice versa. Or it can be prescriptive based on policy. Say, I am expecting this specific accelerator ID or switch ID to be present on a given UALink link, and then verify that state and take actions accordingly. And then, of course, vpod management, effectively create and delete vpods that translates towards updating port membership for vpods and setting up routes. And with that, I'll hand off to, oh yeah, there is this aspect as well. So control RPC specifically is an extension into the GNMI service. You should be able to find the GNMI proto itself. It's all open source. It's part of the open config standards forum as such. We've added a control RPC, and that will be published as part of our spec. So GNMI includes all the existing management RPCs and telemetry RPCs otherwise, and we have not changed that. We reuse that in UALink. So effectively, the control RPC is really a peer-to-peer control plane protocol between the pod controller and the SMA, and the overall sequencing of how the control plane works is defined in the spec. You can find the details on that. And with that, I'll hand off to Justin to go into the rest of the details.
Sure. So similar to what Arun spoke about the switch platforms, a system node has a local node management agent, speaks Redfish to the pod controller. There was a question in the chat, is there any sort of interface defined below the node management agent? And at the present time, we have not defined any sort of interface below there. There's no register definitions or anything like that. So that's up to your specific implementation. Work with accelerator and node vendors would work together to develop that sort of interface. We are not making any particular requirements there. And Arun hinted at this earlier, but the we have defined a switch abstraction interface, again inspired by the OCP SI, that allows for interoperability of switch vendors. The switch abstraction interface is a set of C APIs that must be met by software running on the switch control processor. Interfaces over to the switch silicon in whatever way is defined by that particular switch vendor, and implements the required APIs, the required functionality that we are defining. We are not defining a physical interface. We are not defining a protocol stack for that communication. We are really just defining the set of APIs that are required to be implemented. So again, our management strategy has really been to enable these user journeys. That's pod topology management, discovery, configuration setup, virtual pod creation, monitoring, control, so that virtual pods can be distributed out to tenants, capacity tracking, reporting, neighbor verification, seeing who's on the other end of my link and validating that everything's plugged correctly, and similar flows that tenants can use. With that, we will be done with the manageability section. The 1.0 release of our spec is on the UALink Consortium website, and these Yang models, GNMI protos, the SI header files, those will be published on GitHub fairly soon. So thank you, everyone, and I will turn it over to Rob to talk about chiplets.
Great, thanks, Justin. Yeah, so I'm Rob Pelt. I chair the UALink Chiplet work group, where we're basically trying to take all the stuff you've just seen and put a specification together let's physically implement it. So where we're at in this journey, we've released the Chiplet 1.0 specification, so that specification aligns with everything you've just seen. Is the 2.0, which just so happens it's the first chiplet specification. The idea behind the chiplet specification is we want to standardize integration of UALink into accelerators and switches so that you can go get, if you're not an expert in the physical layer, but you're an expert in accelerators, you can go get a UALink chiplet, put it onto your accelerator, and now you're into the UALink ecosystem and get all the good stuff we've just talked about. So the way we've looked at it is we decided to sort of break the first pass of this into two formats of chiplets. I'll show you what the chiplet looks like in a second. But there are basically sort of two variants of that chiplet. And you can just think about them as pure bandwidth. One's an 8 terabit per second chiplet, and the other one's a 16 terabit per chiplet. If you break that down a little bit further, if you remember from Derek's presentation, UALink is often found in stations, and so it's really a 10 and 20 station chiplets. And then you can see in this table, you can see some of the other factors of it, but basically think of it as 8 terabytes and 100 millimeters and 16 terabytes and 200 millimeters. Now those are target areas. We don't have any implementations that are public yet, so we don't have any real numbers, but that's kind of what we're targeting, so people get an idea of what the sizes might be. The UALink chiplet is built on the UCIe 3.0 specification. UCIe is sort of the default die-to-die open standard that exists. So one of the things we did was to make sure that was highly efficient and to keep the UCIe speeds down. So you can see we're basically to deliver the data across for about 93% efficiency. And we're in the 32, 33 gigabit UCIe range, which is not the top end of UCIe, but certainly very comfortable. It's been at 32 gig has been in the spec for quite some time. In addition to just getting pure raw bits across the interface, we also do there's RAST and power thermal management information in there about how to do that, how to sort of standardize that for the chiplet. And then there's clocks, resets, events, everything else you would need to actually make a chiplet work and make it compatible. So here's a little bit more breakdown of what it looks like. So if you remember from Derek's slides, there are the three stack, the four major components of the stack. There's the UPLI, there's the TL, there's the DL and the PL. What we've done is we've split the chiplet boundary between the TL and the DL. There's a lot more information in the spec about why we do that, but basically the TL is already really good at compressing UPLI, so we don't want to redo it again. The way we do this is we group two UALink stations, each of these 800 gig stations, and we put those into over a single UCIe interface. So you can think of this as just stripes of two stations, one UCIe going across. And then for management of the chiplet, there is basically one management for the domain for the whole thing. So we're not managing each station independently. It's basically try to keep the overhead down. We'll have one amount of management for the entire chiplet. But if I walk through the top to the bottom, you can see this is sort of an accelerator example. An accelerator will probably have some native bus. You'll want to convert that to UPLI, so you can use the standard UALink stack. Once you convert it to UPLI, there's the spec defines how to take UPLI and turn it to TL, and TL then is basically a set of fixed size 64-byte flits. We take that TL and put it into what we call the flitterizer. Basically, this is just taking TL flits and packing them into UCIe flits. I have more information about that on the next slide. And then once you have UCIe flits, you can put those across the the UCIe interface. You can see we've standardized on UCIe by 64. Well, if folks are familiar with UCIe, it's agnostic to whether you're using the standard package or the advanced package. I guess I should have said before, the sizes I quoted before were for standard package, which would be a bigger size. And then you get it across to the UALink chiplet, and then you basically do the reverse on the other side. You take the UCIe, turn it into TLs, and then the TLs go to the DLs, and then DL to PL. So basically, we're just inserting this UCIe. We've grouped them into two station groups, get it across, and a centralized management. I won't go through this in a lot of detail, but one of the key things to realize is that TLs are fixed flit sizes. UCIe is a fixed flit size. UCIe has some overhead. To get the TL across, we have overhead. So what we do is we take the TL data and we pack it in as well as we can into a UCIe flit. So this picture at the bottom left is the UALink, is the chiplet format. It's based on UCIe. Format 6, if people are familiar. And so what that does is allow us to keep putting in TL data. So that's TL link, that's the TL actual data, and then a header for it. And then that goes across. As you can see, it doesn't fit quite right because there are 3.7 TL flits per UCIe flit. So what we get is this rotating pattern of where the flits start, where the TL flits start. But it's a fixed known pattern. It's known at time 1, and you could figure out based on the number of flits where everything is. So it's pretty easy to track. So this picture on the right, every color is basically a separate TL flit, and you can just see how that is rotating across. Let me get to the last one. So one thing to realize is that so Dave talked a lot about resiliency. One of the things that UCIe introduces is that it has two things that you have to worry about. One is that error correction is done over UCIe through replay. So there may be times when there's an error and the UCIe has to basically go back to the transmit side and say resend this data. So we have to take care of that. And the other one is that UCIe may go into a retrain mode. It's supposed to be rare, but it can happen, in which case that one takes a while. So we have to make sure the whole link is resilient to that. It stops the link, but at least you're not losing the link. So that's kind of the idea. So we want to be tolerant to retries so that they're sort of transparent to the data that's going across, and then we want to be tolerant of reinitialization of the UCIe or retraining. So there's multiple credit loops that do that. I won't go into detail. The existing credit loop that in UALink is basically at the TL level. So that one's still maintained, but we had to add a few more basically to cover those things I talk about. And if you look inside the specification, you'll see there's a lot of details about the calculations and what buffers are needed and delays and things like that. So I went through that kind of fast, but basically the idea here is that we split it nicely between the TL and DL boundary. So now you can have this UALink chiplet, and then if you're updating your accelerator or switch, you don't really have to change the chiplet. It's nice and standardized. UCIe flow we tried to keep as efficient as possible. I showed you the two form factors. And then basically, it's a the spec is done. It's available. We'll be adding more to it, for more compatibility, more features in the future, but it is it should be good enough for folks to build right now. I forgot to put the link on here, but if folks are interested, we'll be doing a deeper dive tutorial at the Hot Internet Connects. Hot Internet Connects is a virtual conference. So you just jump online and get it. We'll be doing a much more in-depth view of the UALink chiplet. And that's all I have, Nolan, so take it away.
Awesome. Thank you, Rob. And thank you everyone for joining today, and thank you to our speakers as well. Unfortunately, it looks like we're all out of time for a Q&A, but we will be publishing a blog providing answers to the questions that we were not able to address today. If you'd like to view the webinar on demand, the recording will be available on the UALink Consortium YouTube channel and the presentation on the UALink Consortium website that you can see here on this slide. Thank you everyone for joining.